Today, we're going to try to do something incredible. Today, we're going to try to invent calculus together. A lot of students struggle with calculus, and the reason why so many students struggle with calculus is because it's taught in a very abstract manner. And in fact, calculus, when it was invented to solve physical problems. Newton was trying to understand how planets rotated around each other and how planets move. So he wasn't just doing abstract math. He was trying to understand something physical and something concrete in the real world. So that's the approach that we're going to take together as we try to invent calculus ourselves. Okay? All right, so let's get started. So calculus can be summarized by two concepts: the concept of the derivative and the concept of the integral. So let's start with the derivative. A derivative is defined by this expression here. And really what a derivative is it's the attempt to keep track of the speed of a function at any given point in time. So if you want to know how a function changes with time, we're going to say the function describes the position of an object. So it could be the position of a car. So you have a car that's moving and it's going to have a position at any given point in time, and we're trying to figure out how to calculate the speed of the car at any given point in time. Well, how do you do that? What you can do is you can document the position of the car at time t, which will be p of t, and then you can document the position of the car at some later time, t plus delta t, and then you take the difference because that tells you the distance the car traveled between time t and time t plus delta t. And then you can divide that difference by the change in time. And this ratio will give you an estimate of the speed of the car at time t, but we don't want an estimate of the speed of the car at time t. We want the exact velocity of the car at time t, the exact speed. And how do we do that? We set the limit as delta t goes to 0, which means the difference in time in which we documented the position of the car, we're going to shrink that interval to be as small as possible. This brings in the concept of the limit. And here's the thing, you might say, well, if you want to know the speed at one point, why not just set delta t equal to 0? Why invent the concept of a limit? Well, the issue with that is that it is improper to divide by 0. So we can't set delta t equal to 0 because we'll have 0 in the denominator. So the next best thing we can do is we can say, well, we're going to force delta t to behave like 0 without actually being 0. So we want delta t to approximate the value of 0 as close as possible without actually being 0. So it's like, okay, somewhat kind of understand what's going on here, but there's still some questions that we have to answer. How do we know that this limit is going to give you something meaningful and real? We have to answer those questions, okay? So that's the concept of a derivative. Now, the second part of calculus is the concept of an integral. Now, an integral is the opposite of a derivative. Imagine that we know the speed of the car at any given point in time, and we want to use that to document the position of the car at any given point in time. So if you have the speed, all you have to do is multiply by the difference in time, and that should give you the distance traveled, which will be the change in the position of the car. So that sounds easy, but here's the problem. Objects don't always travel at the same speed. So that's going to be an issue because velocity times time equals distance traveled is only true if the velocity is constant within that time interval. But velocity is not always going to be constant within a certain time interval. So what can we do? We can chop up the time interval into n pieces. Some big number n, we want to chop the interval up into tiny pieces. The speed within these intervals is going to be relatively constant. And because the speed within these intervals are going to be relatively constant, use that speed to multiply by the thickness of the interval, which is the duration of time, and add them all up to get the total distance traveled. But this is going to be an approximation. But our approximation is going to get better and better as we set the limit as the intervals go to 0 and goes to infinity, because we chop that finite interval up into infinite pieces, and within each of these infinite pieces, the velocity is going to be constant, and therefore we can multiply that constant velocity times the thickness of the interval, add them all up, and that should give us the change in position as a function of time. And that is what this expression is telling us right here. All right, so let's go ahead and analyze these two things together. So first, we're going to try to make sense of the derivative, because once we can make sense of the derivative, the integral is going to follow smoothly from that. All right, so we're going to try to keep track of the speed and the position of an object. Okay, so if we want to keep track of the position of an object, that's easy to do, right? All we have to do is create a linear track, put tick marks on that track and label them. And then all we have to do is just allow the object to move and keep track of the position of the object with time. We document the time and we document where the object is. And that will give us the position function, right? So position is easy to do, but speed is where things are going to get hard, because In order for you to measure speed, you need 2 different periods of time. But calculus tells us that we can actually calculate the speed at a single point. So let's see if we can derive that for ourselves. So if I document 2 positions of an object, some initial position and some final position, I can calculate the average speed of the object by taking the difference between the final position and the initial position and dividing by the amount of time that separates these 2 positions. This is the average speed within the interval. It doesn't mean that the object was traveling at this specific speed throughout the entire interval. The speed profile of the object could look like anything, basically. If you know that the object was not accelerating, it was moving at a single speed, then you would be correct to say, not only is this the average speed of the object, but this was the speed of the object at every point in time within this interval. That would be correct. But that's only if you can guarantee that the object was moving at a constant speed. So we can already tell it's going to be hard for us to assign a speed to a specific point in time. So if we're going to try to document the speed of an object at any given point in time, we're going to have to make some assumptions about how the object moves. So for example, we know that the object cannot teleport. An object can't be at one position A and end up at another position B without crossing every position between A and B. The object can't be at A and just disappear from A and end up at B. This is a requirement of continuity. So we require that the position of the object changes continuously throughout the interval. And we also have that requirement for the speed. You can't be doing 20 miles an hour and then suddenly be doing 40 miles an hour without ever crossing all the speeds between 20 and 40. So we're going to impose those requirements on the motion of our object. And those requirements are the requirements of continuity and differentiability. So those are the mathematical terminology, but the colloquial terminology is that the object moves in a continuous and smooth manner. So the position function that describes the motion of our object has to be continuous and smooth. And this right here is where we gain our big insight, because where have we studied smooth and continuous functions before? Oh yeah, algebra class, polynomials, right? If you say that a function is smooth and continuous, that basically means that it can be written in the form of a polynomial. Perfect, now we're getting somewhere. So we're gonna go back to our track and we're going to track the position of the car at some time t and at some later time t plus delta t. And we know that we can write the position function of the object as a polynomial. All right, so we document the position of the object at some time t, and then we ask what's going to be the position of the object at some later time t plus delta t. Well, then we can write p as a function of delta t, which is the later time. We can write this as a polynomial of delta t. It's going to be equal to a constant a sub 0 plus a sub 1 times delta t plus a sub 2 times delta t squared, etc., all the way up to some order a sub n times delta t to the n. So this is going to be the position equation of our object. Now we can go ahead and calculate the average speed between t and delta t. All right, and when we go ahead and simplify this, the a sub zeros cancel and we're left with a sub 1 times delta t plus a sub 2 times delta t squared, etc., all the way up to a sub n times delta t to the n. And now we can go ahead and divide by the delta t. And when we divide by delta t, we get a sub 1 plus a sub 2 times delta t plus, etc., all the way up to a sub n times delta t to the n minus 1. And now here's the beautiful thing. If we set delta t equal to 0, we get the speed at time t. And the speed at time t will be equal to a sub 1. So this right here tells us that it's possible to have a speed at a single point. But we still have to be careful not to set delta t equal to 0. Because remember, we arrived at this equation from the first 2 equations up top. And in those equations, delta t was in the denominator. And remember, we can't have 0 in the denominator. So we still can't set delta t equal to 0. So instead what we're going to do is we're going to set the limit as delta t goes to 0. So we want delta t to be as close to 0 as possible. Then all these other terms are going to cancel out and we're going to be left with a sub 1. And it doesn't matter how large your acceleration is. You can make a sub 2, a sub 3 as big as you want. We can always choose a delta t that's so small that all those terms go to 0 and we're still going to be left with a sub 1. We're just left with the first order term. That's really what a derivative tells us. All right, so now that we've learned how to calculate the velocity equation from the position equation, let's work backwards and learn how to calculate the position equation if we're given the velocity equation. All right, so let's assume that we know the speed function between some time t0 and some later time t. And now we want to know how does the position change from the time t0 to time t. Well, remember, the position at some later time t is going to be equal to the position at some earlier time p0 plus the average speed times the difference in time. We can create intervals so small such that the function is a constant within these time intervals, right? Which is what we already showed with the derivative. So we're going to use that to our advantage to chop up the speed function into these tiny intervals such that the speed is a constant within each of these intervals. And since the speed is a constant within each of these intervals, we can multiply these speeds times the difference in time of these intervals, add them up, and get the change in our position. All right, so all we have to do is take the time difference between t0 and t, divided by n, chop it into n parts, and set the limit as n goes to infinity, because then if we chop it up into infinite pieces, we get very, very narrow intervals such that the speed becomes constant within these intervals. And if the speed is constant within an interval, it is accurate to say that the distance traveled is the speed times the time duration of the interval. And we do all this by just setting the limit as n goes to infinity. When we set the limit as n goes to infinity, this becomes an integral, which we write as an elongated s. So it's the integral from initial time t0 to some later time t of the velocity times dt, the duration of the intervals. And this interval is going to give us the change in our position function from some position p0 to some position p of t. And this right here is what is called the fundamental theorem of calculus. It is the link between the position function and the velocity function. So the velocity was the derivative of the position function, and the position function is the integral of the velocity function. And this relationship between position and velocity is what calculus was all about. And we have just derived it for ourselves and made sense of it as best as we can. All right, so hopefully that made sense for you guys. Let me know if it helped you understand calculus a little bit better. If it did, go ahead and give the video a like. Go ahead and leave a comment in the comment section if you have any questions. And as always, look out for our videos every week. With that said, I'll see you guys in the next one. All right, bye-bye.